Okay, so we are in Chapter 7 of second edition of Statistical Rethinking, and here we'll be tackling question 7H1 as well as 7H2. Before running any of this code, make sure that you have installed and loaded the Rethinking package in R here. And with that, let's get going. Okay. So here is the question to 7H1, and I'll let you read that for yourselves, but the synopsis is this figure right here was drawn, probably hand-drawn, in an article occurring in the Wall Street Journal at some point in 2007, I guess, where the x-axis is tax rate and the y-axis is tax revenue generated. And the argument that was being made here was that there's kind of a U-shaped curve to the relationship between tax rate and revenue. But you can see that this quote-unquote line of best fit really is not the best fit. It has just gone out of its way to hit this high point up here. Okay, so what we are asked to do here is to actually examine this data and then fit both a linear and a curved model of our choice, and then compare the straight line model versus the curved model with WAIC or PSIS or whatever. Okay, and then to make some conclusions about the relationship between tax rate and revenue. So first let's load the data and get a little bit of a look at it. And so it's just this, it's just a data frame with tax rate and tax revenue, and that's it. Okay, and so now we're going to fit a couple of models. We'll fit a line model, a straight line model, as well as a curved model. And but the first thing that we'll do, so if we're using a Bayesian model, we need to establish priors for our parameters. And I don't have a good sense of the of what good priors would be. And so the first thing that we'll do is just standardize our variables with the standardized function, which is part of the rethinking package. And so I have T rate for tax rate and T rev for tax revenue. Okay. And so the models that we'll use, so here I just have a straight linear regression with one regression variable. And then here we'll just use a quadratic polynomial. You might use different curved models, but this is just what I'll play with here. Okay. And you can kind of look through the model here if you want and look at the priors and everything. But we're going to go through and we're going to run these. And we could look at the outputs, the summary outputs with PSI, but really what we're tasked with here is to compare the models with our overfitting metrics. So, and I'm going to use PSIS. We could use both WAIC, or you could use WAIC, but I'm going to use PSIS because it will do some things for us in the next question. And just for continuity, I'll use PSIS. So I'm rounding here. So that's what the round function is. But the major point here, or the major command, is compare. And I have my two models. And then I'm using PSIS. Okay, and I'm just rounding to 2 decimal points to make it readable. Okay, and so here's our output. All right. So here we have it for the line. Okay, so this is the PSIS score for the line, as well as for the curved. Okay. And in this case, we see that that the line receives the bulk of the weight. Okay, in other words, it's so the line fit is performing better than the curved fit. And there's a couple of things here. So for each of these models, there are high Pareto K values. Okay, we'll talk about what that means in a minute. Or well, actually, let's just talk about it right now. So high K value. So every observation in these models is receiving a K value. And K values that are high, and greater than 1 in this case, are heavily influential in the fit of the model. And so if we have an influential data point that is really driving the fit of the model, it may mean then that our model is going to have a tough time generalizing to other data that it hasn't been trained on. Okay, there's something else that happens here. Let's see if I can get it to do it. So if I run this a few times, notice that we're getting different outputs. Now curved is performing better than line. I'm not really sure what's going on here. There's obviously some kind of stochastic process when this is being calculated, but I presume that this very high K value is throwing a wrench in the works. If you know exactly what's happening here, why we can get these to flip-flop on consecutive runs, so now it just flipped again. and the weights are very different. But if you know what's causing that, I would be very interested. So that'd be great if you left a comment somewhere. But anyway, so I don't really know what to conclude then about the relationship between tax revenue and tax rate, especially because the two relationships that we've posited so far, our metric for comparing them is pretty ambivalent. It will, depending on which run of the PSIS command that we're using, we can flip-flop which one is preferred and by how much according to the weights. So instead, I'm just going to move forward into 7H2, and because some of these issues will be resolved in 7H2. So in 7H2, we want to examine the highly influential point that is being pointed to with these warnings here, to try to identify it, and then refit the data, but using robust regression if you're not with the student t distribution, and so we'll do that, and then to re-examine the relationships, or the PSIS or WAIC scores, and it also asks us to determine how much of a curved relationship depends on the outlier point. So the first thing that we'll do is we'll look at these PSIS scores in a point-wise fashion. You can also do this with WAIC. The reason I'm using PSIS, if I haven't commented already, is because the PSIS will actually give us this warning when there are values that seem to be driving the fit of the equation. The WAIC command does not. So anyway, so when I run this, I get the PSIS breakdown for each of the observations here. I think there's 29 observations here. Okay, so here's the individual PSIS scores, and already we see one pointing out, but the one with the very high K value is here. Okay, and so this happens to be observation 12, I think if you count down by 12. Okay, so again, it seems to be highly influential, has a K value greater than 1, and that means that it's driving the fit of the regression to a fairly high extent. Okay. So here, when I first ran this, it was a K value of 1.92, but either way, it's a high K value. Okay. So I'm not really, so in the question, I'm not really sure what is meant by how much does the curve relationship depend on the outlier point. In my mind, one way that we could, the curved relationship that's found by the model, it is the extent to which it depends on this 12th data point is represented in some way by these values here, okay, by the PSIS breakdown of the 12th observation. But I don't really have an intuition for what these values mean in terms of answering that question, other than it happens to be a very influential point. One thing that it might occur to us to do is to rerun this same model, but omitting data point 12, and then comparing the PSIS scores between the full data set and the truncated data set with PSIS. And that would seem to be an intuitive thing, but there's a problem with that. And the problem is that when we use PSIS or WAIC or whatever, we need to make sure that we've trained the model on the exact same data set. And here we are explicitly not training on the same data set. And so the scores are going to be, they're not going to be comparable in that case. So instead, what we could do is we could run the model on many truncated data sets, one truncated data set for every data point. So we could run the model on 29 different data sets where each data set is unique because it will drop one unique observation. Okay, and so with QAP models, we can actually do that with the CV QAP function, which stands for cross-validation QAP. Okay, and then so that's what I'm going to do. So I'm going to have all of the observations, so that it'll be the observation that is dropped, its cross-validation score, which again is not PSIS or WAIC, but it's just another metric to find kind of influential data points. And then so we'll look at the data frame that's created, as well as a plot of the cross-validation scores, leaving out individual observations. And this takes a second to run. Let me pause it. Okay, so we're back. So what we have here is, we've created a data frame with the different observation, and each one of these is the first observation is dropped. Okay, and so what is basically the error of the model? The second observation is dropped. What's the error of the model, and so on and so forth. And so then, so now we see when we go all the way down to number 12. Okay, when the 12th observation is dropped, what does that do to the fit of the 12th data point when we've trained the model without the 12th data point? Okay, and we see a very large error here. Okay, and so we can kind of look at the magnitudes of the consequence of dropping each one of these data points, right? And we see that number 12 here has a huge magnitude here. Okay, so all of this has been a roundabout way of trying to answer how much is that quote-unquote outlying or heavily influential data point affecting the fit of the curve. Okay, and so the way that we've done it here is we've dropped every observation and looked at the corresponding consequence of that, and we see that when we drop that heavily influential point, that it induces a large error when we then go and try to estimate that point. Okay, so in other words, it would seem that that one point is really having a major impact on the fit of our models. Okay, so finally, the last thing that we are asked to do is to use robust regression with a student t distribution. And so we have the exact same models that we had before, but now we're using a t distribution instead of, whereas this was a normal distribution, we're using the student distribution, and we're specifying 2 degrees of freedom. Okay, 2 degrees of freedom makes the t distribution very wide, very variable, I guess. So the higher that number is, the more degrees of freedom, the closer it approximates a normal distribution, so it gets less variable. Okay, and so then I'm going to again compare everything. Okay, I'm going to compare the previous models as well as the t models that are both the line and the curve. Okay, and we're going to compare all of these. Okay, so a few things here. So we can actually run this several times. Okay, so the previous time the best scoring model was the curved t. Again, it's the curved t with about the same weight. I run it again, and the best model will be curved t. Okay, and so now we've kind of apparently stabilized whatever was happening when initially we were transposing m line and m curved back and forth depending on the run of the PSIS command. So what we have is that the best fitting model of the ones that we've used is a robust regression. T is a student t distribution with a quadratic term in it. Okay, and that seems to be the best fit model that we have here. Also, depending on the run, you'll see that we get so we have 2 high k values, but that's inevitably going to be from these 2 models right here. Okay, and every once in a while you'll get a warning. Let's see if we can provoke it. Nope. One more time, and then I'll quit. But okay, that didn't work. But once in a while we'll get a warning that a k value is greater than, and I've seen 0.5 here, so it's a less severe warning. But again, suggesting that there may be one of these outline points. But the bottom line here is that with this robust regression, we get better PSIS scores, meaning that the robust regression is expected to generalize better than the non-t distribution regressions. Okay, that's it.